Hello everyone, I hope you're fine. Today we are just David Diaz and myself, Santiago Lopez. We are the group number one from the section two, and today we are going to talk about the practice two, visco reduction petroleum. Okay, guys, here we can see the sequence that we will follow in this practice. First of all, I will talk to you about the introduction, what we will make in this practice, and why. After that, David is going to talk you about the methodology. Then I will show you the results. We are going to discuss and analyze the results. And finally, we will make a conclusion about this practice. Okay, what is viscosity? Viscosity is a physical property that describes the resistance of a fluid. It can be a gas or it can be a liquid. The follow or the form when a force or shear stress is applied to it. In other words, viscosity measures the skyness or fluidity of a fluid and determines how easily a fluid moves through a conduit or moves around an object. There are two main types of viscosity: dynamic viscosity, this is the absolute viscosity, and kinematic viscosity, that is the relative viscosity. This last is related between the absolute viscosity and the density of this fluid. Finally, the viscosity is a crucial property for industry and science since it affects the way fluids behave in a variety of situations, such as the transport of hydrocarbons. But why I'm talking about viscosity and why we need to reduce it? Okay, as chemical engineers, we have a situation. The main factor to reduce the viscosity is found in the asphaltants. The asphaltants are large groups of heavy organic compounds that impede the transport of petroleum. So we need to transport crude oil by pipeline, but the asphaltants are preventing that. So obviously we need to reduce the viscosity of oil. But how we will make it? Okay, we will use properties from the asphaltants and dissolvents, and they are viscosity and polarity. These two properties affect the colloidal structure from the hydrocarbons.
Okay, now for the methodology, we will have two principal steps that will be the mixing phase and the rheological analysis. And we will have an experimental design that will be with six treatments of two solvents used, that will be acetone and toluene, and three levels of concentration that will be 5%, 10%, and 15%. Okay, now for the mix process, we will have three steps. The first will consist in put the crude oil in the beaker. Then we will put the chosen solvent in the beaker that in the case of my group was toluen at 10%. And finally, we will mix with the wood stick until we observe a homogeneous mix. And for safety purpose, all this phase should be done in the extraction cabin. Okay, for the last step of the methodology, we will have the rheological analysis that will consist in four steps. First, we will add the mix that we had in the previous step in the rheometer. Then we will move the geometry down in order to get a 5 millimeter gap that doesn't touch the floor of the rheometer. And then we will set the method of the rheometer that will be steady state flow, shears range between 1 and 100, 5 steps, and a temperature of 20 centigrades. And for the last step, we will get the plate down and press play to let the rheometer work.
Hi again. Let's talk about the results. So follow me. After making the methodology, the rheometer will give us this information. This is an example from the results because there are several tables, but this example have the crude oil or practice solvent 10%. So the columns are the same, obviously different the data, but the most important columns are the shear stress, the shear rate, and the viscosity. So I am going to take the time to explain every column. First, the shear rate. The shear rate is the speed at which the layers of a fluid move past each other due to a applied shear stress. So it's obviously that the units have to be one this time. So let's continue with the shear stress. The shear stress, the units are pascals because shear stress refers to the force acting in a plane parallel to the surface of a material, causing relative slip between the particles of the material. So, or it measures of the force per unit area applied to the former material. And finally, the viscosity, obviously, is the most important because we are contrasting if we can reduce it. And the viscosity, pues, is the property of material that describes its resistance to flow when subject to a shear stress. Specifically, we have seven tables. The first is the crude oil, and the rest of tables are our two diluents divided in 3% of concentration, 5, 10, and 15%. So what we will make? We take the data and vectorize it in MATLAB. Then we'll perform a comparison of viscosity with shear rate, and shear stress with shear rate. What we have here, this is our first important graph because it's making a contrast between the shear stress with the shear rate. We can make quickly conclusions or observations. Practically, the crude oil doesn't have a shear rate. And for example, the concentrations, the major concentrations that are 15%, have the more shear rate that they are toluene and acetone at 15%. Finally, our second graph is making a contrast between the viscosity and the shear rate. So it is important. We can see the higher viscosity that is in the crude oil that it is in traded by the diluents. So we can make conclusions that the concentrations and the kin of diluents is making a difference affecting the viscosity. Finally, for both graphs, the straight lines represent the behavior of structures that follow a Newtonian model because it isn't making a curve or a quadratic structure. Instead, it is a line sequence. And obviously, we can see that the lowest viscosity is and the more shear rate is assigned by the toluene of 15%.
Okay, and finally, for the conclusions, we can conclude that it's possible to see that the viscosity is reduced in all the diluents that we used in the lab. The lines of the graph follow a Newtonian behavior, and the best viscosity reduction was achieved with 15% of toluene. And finally, as a principal conclusion, we can say that the toluene is better than acetone to disperse and dissolve the asphaltene molecules. And we think that that happens because of the polarity of the solvents that we used. For example, in this case, the toluene it's non-polar and the acetone it's polar. So that's the reason why we think that toluene has a better solubility with the with the asphalt tens of the oil that we used. And we can reflect that in the graph that we got in the results.
The reference, both from the PDF, the first from the behavior of the graphs, and the second one is just to know how is the model structure between the toluene and the acetone. Well, here we finish the presentation. Thank you so much for listening and see you the next practice. Goodbye.